Welcome to Math with EJD. In this video, we still continue with partial differential equations as we look at heat equation once again. We've talked about heat equation a couple of times, but now we're looking at heat equation and fundamental solutions. So let's go. The first thing is, once we review the idea of heat equation once more, though we've talked about it a couple of times. So the heat equation is a partial differential equation that describes the distribution of heat, or if you like, temperature in a given region over time. So the region is space and time is time, right? And that is why it has to be a partial differential equations. Okay. Uh, it models how heat, it models how heat diffuses through a medium. The general form of the heat equation in one spatial dimension, in one spatial dimension is partial u, partial t equals alpha partial squared u, partial x squared. Okay, where u of x comma t is the temperature at position x and time t. Next, alpha is the thermal diffusivity. That is a constant that depends on the material. Then we have partial u, partial t, which is the rate of change of temperature with respect to time. Then we have partial squared u, partial x squared, which is the second derivative, of temperature with respect to space, representing the spatial distribution of temperature. Okay, now this equation, assumes that the medium, that is the medium in which heat is flowing, is homogeneous and isotropic. So isotropic means that properties are the same in all directions. Of course, this is a simplifying assumption because this may not always be true. So properties are the same in all directions, and that heat only diffuses, heat only diffuses, not generated. So it's not like a new heat is generated apart from the one already in the system. So not generated or consumed. So it's just movement of heat in the medium. Okay, at this juncture, let's switch over as we have this here. And then let me go for green now. Okay, so let's talk about derivation of the heat equation. How do we derive the heat equation? Derivation of the heat equation. So the heat equation can be derived from Fourier's law of heat conduction. So you see Fourier is everywhere. Fourier's law of heat conduction, which states that the rate of heat flow, at the rate of heat flow through a material is proportional. The rate of heat flow through a material is proportional to the negative, negative of the negative of the temperature gradient. So that tells us that Q is equal to minus K partial U partial X. Okay. This is the Fourier's law of heat conduction in brief. So the rate of heat flow, Q, through a material is proportional to the negative. So technically, we have that Q is proportional to minus of the temperature gradient, partial U partial X. Okay. And then we now have Q equals minus K partial U partial X. So that K now will just be a constant. Okay. So we say where Q is the heat flux. Heat flux is the amount of heat flowing through a unit area. Okay. Next, you have K to be the thermal conductivity. K is a thermal conductivity, which is a material property that depends on the material. Okay. And then partial U partial X is the spatial temperature gradient. Spatial temperature gradient. Okay. So now by applying the conservation of energy principle, conservation of energy principle, we get the rate of change of heat in a small segment of the material. Okay. If we consider a small segment of the medium between x and x plus between x and x plus a small delta x, the amount of heat entering the segment at x is minus k partial u partial x, and the amount exiting at x plus delta x is minus k partial u partial x plus delta x. Okay, now the change in temperature, the change in temperature over time is the difference between the heat entering and leaving the segment. So, and then that will now be partial u partial t equals alpha partial squared u partial x squared. Okay, this is the heat equation where alpha is equal to k over rho c, with rho being the density, of the material, and c being its specific heat capacity, Okay, so with that done, can we move over green here? And then I can go to something I've not used for a long time. Let's say this now. This. Okay, so let's talk about fundamental solutions. Fundamental solutions. So, we are talking about heat equation and fundamental solutions. So the fundamental solution of a partial differential equation is a solution that represents the response of the system to a point source, which we can also call an initial condition. So for the heat equation, the fundamental solution is the temperature distribution, caused by a point heat source applied at x equals 0 at time t equals 0. The fundamental solution can be derived using the method of Green's functions. Okay, so for the heat equation now, for the heat equation, the fundamental solution g of x comma t is given by the Gaussian function. It's a popular one, Gaussian function, which we use for normal distribution. That is g of x comma t equals 1 over square root of 4 pi alpha t, then e raised to power minus x squared all over 4 alpha t. I mean, it looks very close to what we have for normal distribution. So g of x comma t equals 1 over square root of 4 pi alpha t e raised to power minus x squared all over 4 alpha t. Okay, so this solution represents the heat profile created by an instantaneous heat source, by an instantaneous heat source located at the origin. It spreads out over time, and the distribution becomes smoother as time increases. Okay, let's switch things up a bit now. As I choose this and then this. So let's talk about application of the fundamental solution. Okay, so to solve the heat equation for arbitrary initial conditions, we can use the fundamental solution and superposition principle. Superposition principle. I think this actually came up also when we're talking about separation of variables method for solving each of those partial differential equations. So this allows us to express the temperature distribution at time t for an arbitrary initial temperature, profile u u of x comma 0 as an integral, which is u of x comma t equals integral from minus infinity to infinity of g of x minus psi x minus psi comma t u of psi comma 0 d psi. Okay, so we can express it this way, where g of x minus psi comma t is the fundamental solution shifted to account for the initial temperature distribution u of psi comma 0. And then we also have that the integral sums the effects of all points in the initial distribution. Okay, let's take one or two worked examples as we bring this to a close. So at this point, let's move on with this, and then I'll go with black. Okay, I go here. So this is like example 1 now. Example 1. So I want to solving the heat equation, with a Gaussian initial condition. Okay, so now you want to consider the heat equation partial u partial t equal partial squared u partial x squared with an initial condition u of x comma 0. Okay, not so fast rather. U of x comma 0 equals e raised to power minus x squared. Okay, and boundary conditions u of plus or minus infinity to t equals 0. Okay, so we want to find the solution u of x comma t. Okay, so we move on. So using the fundamental solution for the heat equation, we write the solution as u of x comma t equals integral from minus infinity to infinity g of x minus psi. Yeah, I have a side problem, if you have already noticed, comma t u of psi comma 0 d psi. Okay, So next we substitute, right? So substitute the initial condition u of psi comma 0 equals e raised to minus psi squared, and the fundamental solution, which is g of x minus psi comma t, equals 1 over square root of 4 pi t e raised to minus x minus psi squared all over 4t. So if we do that, what do we get? We get u of x comma t, which is integral from minus infinity to infinity, 1 over square root of 4 pi t e raised to minus x minus psi all squared all over 4t, then multiplied by e raised to minus psi squared. Yeah, I don't mind my psi, it's really messed up. Psi squared d psi. Okay, so we see that this is a Gaussian integral. It's a Gaussian integral, and it will be a lot of trouble solving it. But after solving, we get the solution to the u of x equals square root of 1 over square root of 4 square root of 1 plus 4t e raised to minus x squared all over 1 plus 4t. So this ends up being the solution when we solve all of that big equation there. So this shows how the initial Gaussian distribution spreads and decays over time. So as you can see, we didn't really, to solve this, it's going to be pretty complicated. Well, after solving, right, we end up getting what we have right here. So that leads us to example 2. Example 2. So this one is heat equation with a step initial condition. So step initial condition. So the initial condition is actually a step function. That's what this is about. So again, we consider the heat equation with an initial condition u of x comma 0 equals h of x, where h of x is the Heaviside step function defined as h of x equals 1 if x is greater than or equal to 0, or 0 if x is less than 0. We can again apply the fundamental solution method. So it means fundamental solution is another method for solving heat equation apart from separation of variables, which we've seen already. like that. So the fundamental solution again is u of x comma t equals integral from minus infinity to infinity, g of x minus psi comma t h of psi d psi. Okay, so that's the fundamental solution. So it's more like we just invoke that and then use it for whatever we want to use it for. So with this now, since h of psi is equal to 0 psi for psi less than 0, the integral becomes, so without going through all the regular stress, right? The integral becomes u of x comma t equals integral from 0 to infinity 1 over square root of 4 pi t e raised power minus x minus psi all squared all over 4t d psi, basically. So that's what that becomes. So, and then we need to know that this integral can be evaluated numerically. Interesting, I'll be implementing that in Python. So you see how Python handles this. So the integral can be evaluated numerically or using special functions such as the error function, yielding a solution that describes the diffusion of the step function over time. Okay. So in conclusion, the heat equation is a fundamental PDE, just like wave and Laplace. The heat equation is a fundamental PDE in mathematical physics that models the diffusion of heat. Its solution can be expressed in terms of fundamental solutions which serve as the building blocks for solving more complex initial and boundary value problems. Okay, through the method of Green's functions. Interestingly, I think 2 videos from now or 3, we'll be talking about Green's function. So watch out. Through the method of Green's functions and superposition, arbitrary arbitrary initial conditions can be solved by integrating over the initial distribution. So the heat equation has numerous applications from modeling heat diffusion in materials to solving problems in finance and population dynamics. All right, so this brings us to the end of this video on the heat equation and fundamental solutions. Now let's look at the Python code for that, for heat equation and fundamental solutions, that is. So if you look at what we did already, here we have to define our Green's function, that's g of xt, and we take alpha to be 1.0, and we define that whole expression here, that 1 over square root of 4 pi alpha t with the exponential part e raised by minus x squared for all over 4 alpha t. So we have all that, and then we define the initial condition, which is minus e raised by minus x squared, if you remember, and then we have the heat equation. I mean, we define a function called heat equation, and we do the integrand because we need to integrate, right, with respect to the initial condition, and then we get our result here. By the time we run it, we can see that whole thing looks like. Okay, so it's taking a bit of time to show up. It should be out now, I think, pretty soon. Yeah, so this is it. So in space and time, so as time varies, when t is 0.1 seconds, it's this blue. When it's 0.5, it's the orange. When it's 1.0, it's green. When it's 2.0, it's red. And yeah, something like red. And it goes on like that. So, and this shows the heat profile, how the heat goes. So, I mean, as you can see, at the initial time, right, the heat is at the peak. As time passes, it reduces across board like that. Okay. Um, that's how that goes. Okay. So, let me know in the comment section how helpful this video is for you. And if you need me to teach a topic or solve a problem, feel very free. And of course, be sure to to subscribe already if you have not subscribed, then hit the notification bell so you can always get alerted each time a new video is released. Then be sure to like and share also so that more people can have access to this great content I have on this channel. Till I come your way again. This, I think we already have 700 videos up there, so a whole lot and more still coming because I mean I have so many things I look forward to putting up here. So you don't want to miss out on any of this. Till I come your way again, keep doing math right. Bye.